Hello, welcome to lecture 2 of Embedded Systems Design. In this lecture, we will be talking in details about modeling of embedded systems. So, in the first lecture, we talked about all the steps right from modeling to design to analysis and its iterative structure to ultimately arrive at the complete design and finally implementation we said last day. So, today we will deal with the modeling of embedded systems in more detail. So, before starting to design an embedded system, we have a rough sketch or idea of what we want to develop. That idea has to be in a structured form specified so that we can do analytics on that, understand if the specifications we just wrote down, we just specified in a way, in whatever way we want to specify them are correct and verifiable. So, this is why formal techniques to modeling embedded systems are required. The major source for this lecture today will be Embedded Systems Design, a Unified Hardware Software Approach, Frank White's book. So, describing embedded systems processing behavior can be extremely difficult. Why? Because nowadays we have started to build very complex embedded systems with very complex functionalities in them, with complex interactions within these functionalities. Why? Because with the increasing IC capacity, the capability of designing functions, very complex functions have increased. And so, we have embedded systems with comparatively simple functionalities like the embedded computing systems in washing machines, small games, etc., to which contains maybe say hundreds of lines of code, to very complex embedded systems like say TV set-top boxes, cell phones, to controllers in automobiles, aircrafts, etc. These may contain hundreds of thousands of lines of code. And when we have this scratchy idea of what we want to develop in our head, it is not formally specified, the desired behavior is often not fully understood. That if I implement this behavior in a certain way, what will be the repercussions on other components of the system? We do not understand that fully, may not understand that fully. So, if we have this specification in this way, are we going to always get a response within, can we through any implementation get a response within say a requirement of 10 milliseconds? We do not know. So, therefore, formal and complete specification of the system is necessary. Many implementation bugs due to description of mistakes and omissions. Now, because if we do not specify formally and completely an embedded system, there are chances that there will be a lot of bugs in the description, omissions and mistakes in the later when we want to further take this specification into design and implementation. So, that effort, so if we have such omissions and mistakes, we have to come back and again change the specification and redesign and do this many times. Now, this effort in design and implementation again and again due to errors and omissions can be saved if the specification of the behavior is in a very structured format. Now, when we have this initial idea of what we want to do, the embedded application in mind, we first generally write in English or some natural language, as we take that as the starting point. However, through English, precise description of what we want is impossible. For example, suppose we want to write a motor vehicle code, we want to have an embedded system for a motor vehicle code as to what are the rules that the vehicle should follow when when moving on the streets, what are the rules that the pedestrian should follow on roads where vehicles are moving. Those set of rules can go up to thousands of lines, thousands of pages of English statements, and still you may not be able to formally and crisply state the exact requirements and specifications. For example, again, let us say that you want to just, if you check a part of the vehicle code of the California vehicle code for crosswalks, we will see that you have to write statements like this: the driver of a vehicle shall yield the right of way to a pedestrian crossing the roadway within any marked crossway or within any unmarked crossway at an intersection except as otherwise provided in this chapter. So, these are the ways in which people have tried to write crisp English language specifications, which is almost always is futile. You cannot write statements which is sound, specifications which are sound and complete. The provisions of this section shall not relieve a pedestrian. So, the first one says that the driver of a vehicle will allow a pedestrian to cross the roadway either in a marked crosswalk or an unmarked crosswalk at an intersection except otherwise provided. So, there will be exceptions to these rules. If those exceptions which will be stated later say do not hold, then the pedestrian should be allowed to cross the road at the junction. The provisions of this section shall not relieve a pedestrian from the duty of using due care for his or her safety. However, in doing so means although the vehicle will allow, this does not relieve the pedestrian's duty. So, he can't just close his eyes and cross an intersection. No pedestrian shall suddenly leave a curb or other place of safety and walk or run into the path of a vehicle which is so close as to constitute an immediate hazard. No pedestrian shall unnecessarily stop or delay traffic while in a marked or unmarked crosswalk. Again, the provisions of subdivision B shall not relieve a driver for a vehicle from the duty of exercising due care for the safety of any pedestrian within any marked crosswalk or within any unmarked crosswalk at an intersection. So, what we just want to say is that here through these sentences, when we are writing rules for how pedestrians should cross or how vehicles should cross in an English language, we are trying to be very crisp, so that exceptions to these rules do not occur, but we can find that these are never, through these sentences we can see that these are never complete and sound. We can always find exceptions to in whichever way we are trying to specify what we want to do in English. English cannot be used for these purposes. This is what we want to say here. All that just for crossing this street, the vehicle code is bigger and it will have much more things to do. So, English is not precise, and therefore, trying to specify in English is futile. So, we need formal models and languages. So, how can we crisply or precisely capture behavior? We can think of languages like C, C++, but computation model is the key. C and C++ are languages, and using those languages we can write a behavior, and that has a model which is called the sequential program behavior. So, if we write a C program, we are essentially we have a formal model, we have instructions. So using C and C++, we are using the sequential program model, which has statements or instructions, rules for composing those statements, how those statements can be composed to express a complete behavior, and semantics for executing them. So, semantics meaning that when can certain sentences, although they are grammatically correct, can be used in a particular context. So, it allows statements, and then it also allows us to iteratively and conditionally execute those statements. This is essentially the sequential program model. Again, another common computation model is the state machine model. It is generally used for control dominated systems. It has monitors for control inputs. So, it has many control inputs, it has states, and it generates control outputs. This is the overall model of a state machine. There are many other computation models, for example, the concurrent program model, and then there are others such as the data flow model, etc., which we will not go into. In this chapter, we will be primarily focusing on the example of an elevator controller. Using this, we will understand the different concepts that we will present in modeling. Therefore, we first present the example here. So, the partial English description of an elevator controller will be like this. Move the elevator. So, what we are trying to do, the physical system is the elevator, and within this physical system there will be an embedded control system which will control the elevator. The movement of this elevator will be controlled by an embedded control system, and our job here is to design this embedded control system for the elevator. Now, therefore, first we have to specify in our minds. So, in our minds we have to first organize what will be the behavior for this embedded controller for the elevator. So, it will be something like this. Move the elevator either up or down to reach the requested floor. Once at the requested floor, open the door for at least 10 seconds and keep it open until the requested floor changes. Ensure the door. So, move the elevator up or down until there will be a request, there will be a global request from somewhere, some request will be there for reaching a certain floor, and then the elevator will move floor by floor, and at each point, at each time it will have knowledge of what is the current floor it is in, and it will move to the requested floor. Once it reaches the requested floor, it will open the door for at least 10 seconds and keep it open until until we do not have a new request to go to another floor. Okay. Up to that, the door will remain open. Ensure that the door is never open when the elevator is moving. Do not change directions unless there are no higher requests when moving up or lower requests when moving down. So, we have a global request right at any given point in time. When the current floor is not same as the requested floor, we are either moving down or moving up to the requested floor. Now, the next what it says that while you are moving up say to a certain requested floor above, we will not change direction unless there are no higher requests. So, you can take higher requests. Suppose what happens is that you reach a floor, you reach a floor going up, and you have a new request which is higher than the current floor, then you can go higher up, but you will otherwise you will go down. So, do not change directions unless there are no higher requests when moving up or no lower requests when moving down. Now, with this English specification, we try to make it a more streamlined. Firstly, we see that it is best to design, we decide within ourselves that it is best to design the elevator controller with two distinct modules. One is a request resolver, which resolves various floor requests into a single requested floor. So, what happens? You have different floors and you have switches beside the lift door for going up or down, right? And you also have different switchboards within the lift to go to a certain requested floor. Now, so therefore, request is coming from outside through your up and down requests outside the lift at various floors, and you also have the request button inside the lift. All these requests together has to be resolved through an algorithm, so that you finally have one requested floor. So, the request resolver resolves various floor requests into a single requested floor, and you have the unit control which moves the elevator to this requested floor. Now, so therefore, the request resolver here, if you see this one, the request resolver, what are the inputs? There are various control inputs which are the buttons inside the elevator. So, B1, B2 up to Bn, these are the n buttons for n floors say within the elevator. Okay. You also have buttons outside outside the lift, just beside the lift door at each floor. What are these buttons? At the ground floor you do not have a down button. So, you have a up one, then you have a you do not have a down one at the first floor. You have an up 2 and a down 1 in floor 1. So, in the ground floor you only have an up 1 because you cannot go down. At the first floor you can either go up to 2 or you can go down to 1. Okay. You have an up and a down, and at the highest floor, at the top floor, you only have a down switch, you do not have an up switch. So, these are the switches, up and down buttons on each floor outside the lift door, and these are the switches that you have inside the lift. The modeling issues that will be discussed in this lecture will be primarily based on the design of an embedded controller which we discuss here. So, what we want? We have a physical system, an elevator, which is controlled by an embedded control system, the elevator controller. Our job is to design an elevator controller. So, before the elevator controller is designed, we just have what we want to do in our head, a scratchy idea. We first jot that down into in an English using an English language description. A partial English language description for an elevator controller can be as follows. Move the elevator either up or down to reach the requested floor. Once at the requested floor, open the door for at least 10 seconds and keep it open until the requested floor changes. Ensure the door is never open while moving. Do not change directions unless there are no higher requests when moving up or no lower requests when moving down. Now, with this description in head, we start our modeling. In our modeling, we first understand and decide that this lift controller should have two distinct modules. One is the request resolver, which resolves various floor requests into a single requested floor, and two, an unit controller which actually moves to the requested floor, which actually moves the elevator to the requested floor. Now this description, this particular specification, English language specification, can now should be transformed through a model to a more concrete specification. And as we said, we have various modeling strategies. One such is the sequential program model. Suppose we want to implement or specify the behavior of this elevator controller through a programming language such as C. Okay. If we do so, we have to first specify what are the input, outputs and data variables associated with this controller. Here we see that we have a data input floor. So, this data input floor will be provided to the embedded controller from the physical system. So, whenever the lift is moving or not moving, at any point in time the elevator controller, the embedded controller for the elevator will have the knowledge of what is the current floor the elevator is in. It will also have bits B1 to Bn. So, these are binary inputs, bits B1 to Bn corresponding to the buttons inside the lift. So, B1 to Bn are the buttons inside the lift corresponding to each floor. So, if we want to go to say the third floor, we will press B3, the switch B3. These are the switches, these are corresponding to the switches inside the lift. At each floor outside the door of the lift, we also have up and down buttons, right. So, at floor 3, we will, if you want to go up from floor 3, we will press the up button and wait for my lift to come. So, these are the up and down buttons on each floor outside the lift door. So, at the ground floor you have an up 1 button, you do not have a down button because you are already at the ground floor. At the first floor you will have an up 2 and a down 1 button. At floor 3 you will have an up 3 and a down 2 button, and so on. At the top floor you will only have a down button, you will not have an up button. So, these are inputs, again binary inputs corresponding to these switches outside the door of the lift at each floor. Now, the elevator controller will output, what will it output? It will generate control outputs up, down or open. So, up will mean that the lift has to go up, the elevator has to go up. Down will mean that the elevator has to go down. Open will mean that the door of the elevator has to open. It will also use the global variable rec which will hold at a given time the requested floor, meaning that the lift has to move to a certain requested floor. This global variable rec will hold at any time to which floor does the lift has to move. This rec will be output by the function request resolver, which we do not completely specify here, but what it will do is that it will resolve from various requests made at the different floors by different people and within the lift. So, we are not bothered about what particular algorithm it will use, it will certainly use certain algorithm, and we do have to specify that, we are not specifying it here. But ultimately at the end of this algorithm, finally we will resolve into a single requested floor where the lift has to move. Okay. This will be done by the request resolver. The other is the unit control function. So, we will write a function or sequential program for the request resolver. We will also write a function for the unit control, this unit control part. So, what will the unit control do? Initially, for the unit control, the output up and down are 0 and the door is open. Why? Because initially it will be at the idle position. At the idle position, the requested floor will be equal to the current floor, and up and down it will neither go up, it will neither go down, therefore, it will be stationary, the lift will be stationary. So, up and down are 0 and the door of the lift is open. So, this is what was required. Move the elevator either up or down to reach the requested floor. Once at the requested floor, open the door for at least 10 seconds and keep the door open until the requested floor changes. So, till the time the requested floor is equal to the current floor, it will just stay in that floor and keep the door open. Now, after that it will move into an infinite loop while the requested floor still remains as still remains same as the current floor. It will just wait in a loop. Then open equals to 0. So, when this is not true, when the requested floor has changed from the current floor and the lift has to move, the elevator has to move to a certain floor, open is set to 0. That means the door of the elevator has to close. Now, it has to decide whether to move up or down. If the requested floor is greater than the current floor, it has to move up, then up equals to 1, else down equals to 1. So, if rec is greater than, it is not equal to, rec is not equal to floor, that is known. If now rec is greater than floor, it is going to move up. If rec is less than floor, it is going to move down. Now, after that, while the lift has not reached the requested floor, unit control will wait. So, it will wait in a loop, this while loop, until request is not equals to floor, until the elevator has not reached the requested floor. Once it has reached the requested floor, again up equals to down equals to 0, because the lift has to go lift will again be stationary, and the door will open. So, open is 1, and then it will wait for at least 10 seconds, delay of 10 seconds, and then it will remain idle for at least 10 seconds. It will the open is then not set to 0. So, open is going to still remain open, but at least 10 seconds it is going to wait there. It is not going to move to a newly requested floor at least before 10 seconds. It is not going to do that for 10 seconds. After that, it can again move. Now, what will main do? The main function of the lift controller, the elevator controller, will concurrently call in parallel both unit control and request resolver. So, request resolver will work independently and concurrently, and it will go on resolving requests and generate a finally consolidated single request. Based on this request, the unit controller will move to the requested floor, and by generating control outputs, unit controller will generate instructions to go to the requested floor rather through control outputs up, down, open, etc. In this process, the unit controller will always keep this floor input, floor data input, it will keep in its knowledge the value of the floor data input. So, trying to capture this behavior as a sequential program is a bit awkward. So, instead, because why is this so? Because this is primarily a control dominated problem. This embedded controller here for this case is a control dominated software that we want to build, software or in hardware, whatever it is. It is a control dominated specification that we want to specify. So, instead we might consider an FSM model describing the system as possible states, their transitions and actions that should occur at each state. This is more easy, because this is how the things are actually happen for our elevator controller. It has states idle when the elevator is not moving. It can go up, it can be in a state going up, it can be in a state going down, it can be in a state door open. Possible transitions from one state to another based on input. It has, so if the requested floor is if the requested floor is greater than the current floor, then you go up. So, you are in an idle state, and then say the requested floor is greater than the current floor, then you go to the state going up using the transition request greater than, using the transition labeled request greater than floor. Actions that occur in each state. So, corresponding to each state you also have actions. For example, in the going up state, the up control output has to be 1, the down control output has to be 0, the O control output, which is the door open, has to be 0, and the timer is also 0. Why we require the timer? We are just coming to. So, using this we can specify an FSM like this. So, in this FSM, let us see that the FSM starts at the initial state of the FSM is this one, idle. It has the name idle. In this state, it stays until the requested floor is equal to the current floor. So, in the self loop it moves, it goes on in this the self loop, it goes on staying in this idle state until the requested floor is different from the current floor, and in this state you have up and down variables, U and D corresponds to up and down outputs. They are 0, and the door open output is 1, and the timer is 0 again. And then if the requested floor is greater than the current floor, you move to the going up state, and then you stay in the going up state until requested floor is greater than the current floor, and in this state your up variable is 1, down variable is 0, open door variable is 0. So, the while going up or going down, the door of the elevator should remain closed. Similarly, when request is less than floor, you go down to the going down state. Okay, you go to the going down state, and in this state you remain until the requested floor is less than the current floor. and in this one the output that it will produce in this state is down equals to 1, all other control outputs are 0. Now, in going up or going down at this state, when the requested floor finally becomes equal to the current floor, you go to the door open state. So, when you are in going up and then the requested floor is no more greater than the current floor, that means the requested floor has become equal to the current floor, you go to the door open state. Similarly, in going down, if the requested floor is no more less than the current floor, then you go to the door open state. In the door open state, your up and down both are 0, so the lift is not moving. Your door is open, so it is 1, and what you do is you set the timer t. So, the timer was 0 in all these 3 states, going up, idle and going down. Now, you set the timer and you move into this self loop until timer is less than 10. So, the door should remain open for at least 10 seconds before it takes fresh requests. Okay. So, it will remain in this state, and then when the timer becomes equals to 10, which means that the timer is not less than 10 anymore, it goes back to the idle state, and in this idle state it will still the door will still remain open until till the time the requested floor and the current floor are same. Again, when the requested floor becomes different based on what the request resolver has told you, then the FSM again moves to either going up or going down. Now, this was an informal definition of how the FSM model works. So, how you specify a behavior using the FSM model. Now, to formally define this model, we do as follows. An FSM is a 6 tuple, where S is a set of states. Every FSM will have a set of states S0, S1 dot dot dot. A set of inputs I0, I1 dot dot dot, a set of outputs O0, O1, a next state function which goes from which is a function of what which goes from the set of states and set of inputs to a set of states, and it has a set of outputs. So, it has an output function. From each state it generates an output. So, at each state based on certain inputs it goes to a next state, at each state based on certain inputs it goes to a next state, that is why it is S cross I to S. H is an output function which goes from a state to output, and S0 is the initial state. Now, the FSM we just built is a mood type FSM. Why? Because it associates the outputs with states. A mood FSM is an FSM where the outputs are solely associated with states, as against mealy FSMs where the outputs are associated with transitions. So, in a mealy type FSM, the outputs are associated with transitions. So, if you are at current state S and you have some inputs, depending on that you will produce some output. So, you have an S, you have a transition condition based on inputs, based on that you go to a certain next state and produce certain output in a mealy machine. In a mood machine you move to a new state and at that state you produce certain outputs. Now, to simplify definitions of FSM, several shorthand notations can be used. A few of them are as follows. Shorthand notations to simplify descriptions. You can implicitly assign 0 to all unassigned outputs in a state. So, if you have not assigned, here we have explicitly assigned a 0 to all outputs at a given state. Now, if you do not want to do that because it is tedious to do, only certain outputs will be 1 and all other outputs will be 0, you can implicitly assign 0 to all unassigned outputs in a state. You can also implicitly AND every transition condition with the clock edge, meaning that many of these FSMs will actually end up being defined as hardware circuitry. And in a hardware circuitry, typically things are synchronized with the clock pulse of a timer. So you can say that implicitly you can AND every transition with the clock edge of a timer, and you don't need to explicitly say that AND timer. As an example of how Moore and Mealy machines are defined, we again go back to the garage counter example that we had discussed in the last lecture. Here you had a garage parking lot where the job of the embedded system is to keep an account at any time of the number of cars in the garage. Now, you can design this as a Mealy FSM or a Moore FSM. Now, the first one here is a Mealy FSM. Now, here at any time the job of the embedded controller is to produce as output the number of cars. So, if you are at state 0 and your up is 1, that means a new car has entered and down is not 0, then what happens? Then you output a 1, because up is 1, you have 1 car in the garage. At state 1 again you have an up 1 and a down 0, then you produce an output 2, that means you have 2 cars in the garage. Now, at state 2 you moved to state 2. So, a state tells me what is the current number of cars in the garage, and at state 2 say again what happens is that 1 car goes out. So, down is 1 and up is 0. If it so happens, then you produce an output of 1, because you go back to state 1 and the number of cars actually is 1 in the garage at this time. So, this is how you can define a Mealy FSM for the garage counter. A corresponding Moore FSM will be as follows. At state 0 you output 0. At state 0 you know that the number of cars is 0 and you output 0. Then you have if you have an up and not down, you straight away go to 1 and you know that you are at 1, that means the number of cars in the garage is 1. So, you output 1. So, here you see that the output is associated with states and not transitions, and hence this is a Moore type FSM. Here in this case the output is associated with a state and a condition. So, here the output is associated and the input. So, if the state is 0 and the up is 1 and down is 0, then the output is 1. So, here the output is associated with a state and input and the inputs. Here the output is associated only with the current state. So, the first one is Mealy and the second one is a Moore type FSM. Now, the FSM description that we just provided here was not actually a simple FSM, but was an extended FSM or a finite state machine with data path, FSMD. So, let us define what an FSMD is. It is not a simple FSM that we just discussed, because of what we will just discuss now. So, FSMD extends FSM. It allows complex data types and variables for storing data. FSMs use only Boolean data types and operations, no variables. So, in our definition of FSMs that we used earlier, we did not have any variables in the definition of the FSM. So, in the definition of the FSM we did not have variables, and all our inputs and outputs were binary. We did not have complex data types. So, these are the two extensions that have been added to the simple FSM for better modeling of embedded systems. So, FSMD is a 7 tuple. It has a set of states, it has a set of inputs, it has a set of outputs, it has variables now, which is new. It has the next state function, which is a function of the state, the inputs and the variables. and then it goes to new state. It has an action function which goes from a state to a set of outputs and variables. So the action function now not only produces output control actions, it also updates variables. Now, in our case, we see that we have variables in this FSMD. We have variables. We have complex comparisons on transitions, such as comparisons. Here these are not binary Boolean. You see that request and floor, they can have data types which are integers, they are not binary. So, therefore, you have allowed complex data types and you have allowed variables. So, I, O, V may represent complex data types, integers, floating points, etc. F and H now include arithmetic operations. So, in our previous case, these were just Boolean expressions. F and H where this S cross I cross V could only be Boolean expressions. Now, you can have arithmetic operations, for example, subtraction some integer variable from another integer variable and update that variable, etc. So, these are now included as part of the FSMD. Okay. H is an action function now and just an output function. Why? Because along with the production of outputs, it can also update variables. So, we don't say that this to H to be an output function in FSMD, we say that as an action function. The complete state now consists of the current state SI and the values of the variables. So, the state in an FSMD or an extended FSM consists of the state and the values of the variables. So, the elevator controller state machine that we had drawn is actually an FSMD and not a simple FSM. Now, we will look at, we understood what is the formal definition of an FSMD and an FSM. We have already drawn an FSM for the embedded controller, but we now want to see systematically how for any such embedded system an FSM can be drawn. So, what are the steps that are required to draw an FSM for a given specification, from an English language specification? How do we come about drawing a structured systematic FSM? So, first is to list all possible states, and so what are my states in the current FSM? My states are idle, going up, going down and door open. So, from the English language specification, first we have to think what could be the states of my FSM. There could be different ways of designing the same functionality. There could be different ways of not designing, there could be different ways of specifying the same functionality. So, we can say that the meaning of the states to be different, but this one is a possible way in which to do. So, we have 4 states here, an idle, going up, going down and door open. We declare all variables. So, what are my variables? My variables here were the floor and the others were inputs and outputs. For each state, we list all possible transitions with conditions to other states. So, for example, for the idle state, we have 2 transitions. We have 3 transitions. One is when request equals to floor, request greater than floor and request less than floor. These are the 3 transitions. So, for the idle state, we have listed down possible transitions with conditions to the other states, or to the same state rather, when we have a self loop. This for the going down transition, similarly we have these 2 transitions, and for the going up transition, for the going up state, we have these 2 transitions again, and then for the door open we have further 2 transitions. So, we have listed down or we have drawn all the transitions separately for all the states with conditions. Then for each state or transition, we have to list the associated actions. So, what are the actions? With each state, the actions are specified for our FSMD through the UDOT for the UDOT outputs, right. So, U is the up control action, D is the down control action, O being the door open control action and T being the timer control action. Now, after that, for each state, ensure exclusive and complete exciting conditions, exciting transition conditions. What do we mean by these two? Ensure exclusive and complete. So, what happens if you do not have exclusive transition conditions? Then two conditions can be true at the same time. So, exclusive transition conditions, meaning that with respect to a set of control units, there cannot be two transitions from the same state which hold true. For example, rec can be either greater than floor, rec can be either equal to floor, or rec can be less than floor. So, you have three transitions, none of which can be true simultaneously. So, if rec get greater than floor, rec cannot be equal to floor. If rec greater than floor, rec cannot be less than floor. So, this transition will be exclusively excited. So, no two exciting conditions can be true at the same time. Otherwise, what will we have? We will have a non-deterministic state machine. That means, you have two possible ways to move from a state for the same inputs. You have two possible ways to move from a state to another state, and it has to be complete. On one condition must be true at any given state, otherwise the state machine becomes incomplete. So, it is not that design cannot be non-deterministic or design cannot be incomplete, but then for a starter we should avoid having non-deterministic state machines, although later on with further practice we will see that non-deterministic state machines allows us certain optimizations corresponding to the design that we will get from this specification may allow us certain this one, but it also open up doors for errors which for a first timer it may be difficult to handle. Similarly, the need for a complete transition function and not a partial one. That means that at least one of the transitions must be taken at any point in time. So, if I do not have rec greater than floor or rec less than floor, at least rec equals to floor, which means that I will have a self loop moving into the idle state again and again. So, one condition must be true at any given time, that is why it is complete. Reducing explicit transitions should be avoided when first learning. Now, we said that the Mealy machine that we considered for the garage counter, the Mini and Moore machine that we considered for the garage counter was an FSM. Now, we said that FSMD allows certain succinctness in the specification of the models. For example, for our garage counter example, we can have that whole big state machine that we had. In that state machine, if we go back in that state machine, we see that we have, let us say that the garage has space for m cars. Then in this one we will have a big state machine consisting of m states, both for the Mealy machine and for the Moore machine, which is a big representation. How can we simplify this representation, make it more succinct? By using an FSMD, a variable. So, now we have a variable which can count from 0 to m. We have an integer variable which can count for 0 to m. We have our up and down pure inputs, which are Boolean inputs for our garage counter. We have an output count. We have an output count which is again an integer, right. So, we have integer outputs, we have boolean inputs, and we have variables. So, this one is an FSMD. So, we have a state, the initial state is this one. At this state C equals to 0. So, the variable is 0, which C represents the number of cards. Now, how do we output? So, at this state, if up is 1 and down is 0, and you have and you have C, okay, and C is less than M, then you output C plus 1. So, at each point in time, at this state C will have a certain value. Initially C is 0, there are no cars in the garage, but at a certain point in time, when cars have entered and cars have gone out, at a certain point in time, this C value will hold. Let us say C equals to 10 at a given time. You have 10 cars in the garage. Now, at that point in time, you have up equals to 1, down equals to 0, and let us say the capacity of the garage is 20 cars. So, C is less than M. So, if these condition, if this total condition, this set, this and the up and not down and C less than M is true, then you output C plus 1. That means, the number of cars will be C plus 1, because up is 1, one new car has come, and you update also the variable C equals to C plus 1. Okay. Similarly, if you are at C equals to 10, so now C plus 1 is going to be 11, and the updated value of count will be C equals to 11. Okay. Similarly, now let us say C equals to 11, down is 1, up is 0, and C greater than 0. Okay. Then the output will be C minus 1, that means one new car has gone out. Therefore, the output should be 1 less C should be equal to 10. That means, currently the garage has 10 cars after one car has gone out, right. Now, what happens when C equals to M, and so when C equals to N, even if one car tries to enter and up is 1, there is no capacity, the garage is full. So, it is not going to output C equals to C plus 1 and update the variable, because the garage can hold at most M. Similarly, if the garage is empty and C is equals to 0, down equals to 1 has no meaning. Therefore, it is not going to output C minus 1 and update the variable C to C minus 1, it is not going to do it. So, that whole M state machine, FSM machine now just can be expressed as a one state FSMD or an extended FSM. So, this is how FSMD extends the power of simple FSMs. So, we saw two ways of designing of specifying embedded systems, two ways of modeling embedded systems. So, one is the state machine model and the other is the sequential program model. How does these two models compare? Actually, two different thought processes go into the design of these two models. In the state machine model, the state machine model encourages the designer to think in terms of possible states that the embedded system can be in and transitions among these states, so that you can find out how these states, how the state changes happen and transitions among these states on all possible input conditions. This is how the state machine model allows us to think. On the other hand, the sequential program model is designed to transform data through a series of instructions. So, we have instructions in the sequential. So, just think of a C program, you have a series of instructions. So, what does it do? It transforms the data by the statements, and it allows us to iterate over these statements using loops, and it also allows conditional execution of statements through ifs, for loops, cases, while loops, etc. So, a combination of iterations and conditional execution is possible through the if, for loops, while loops, switch cases, etc., and the statements themselves go on transforming the data. So, the sequential program model is designed to transform data through a series of instructions that may be iterated and conditionally executed. So, state machine description excels in many cases. When you have control dominated systems, state machine is a very easy, succinct way of simple way of expressing, and it becomes much less cumbersome than a sequential model. So, state machine often are a more natural means of computing in those cases, not due to graphical representation. So, a state machine would still have the benefits of simplifying the way you can specify the behavior of an embedded system, even if it is used in a textual form. So, we need not have circular states, circles as states and arcs as transitions. We do not need to draw it like that. We can draw it in the form of a state table, where we have an entry for each table with inputs, outputs specified, right. We can represent it in the form of a state table, and it will still have the same expressive power, right. On the other hand, the sequential program can be represented through a graphical representation for a flow chart. So, it does not matter whether you are representing it textually through a textual language or a graphical language, but for certain types of embedded systems, state machines are a very natural way of expressing such systems, expressing the behavior of such systems, and therefore, in those systems state machines will be more beneficial than sequential program model. So, FSMs, so constructing, it is the sequential program model has traditionally been used. So, there are many tools for sequential program based specification and further compilation from that. So, you have high level synthesis tools which allow you to specify in VHDL for hardware description, let us say, and then there are automated tools that will take the behavior to the complete design of the circuit to the hardware circuit up to the fabrication level. So, once you specify the VHDL code, there are a set of tools which will take you to the hardware circuit finally. Okay. Similarly, there are other tools which start from the sequential program model, but then so despite the benefits of the state machine model, most popular development tools use the sequential programming model, which works with C, C++, Java, ADA, VHDL, Verilog, etc. Development tools are complex and expensive, therefore, not easy to adapt and replace. So, if we now certainly say that we will use this diagrammatic FSM and we will draw diagrams, and from there you build it, it is again a separate process, and we have to do away with all the tools we have designed thus far. So, what we do instead is that we use two approaches. We have a front end tool in which we draw an FSM based model using a diagrammatic approach, and then there will be an automated mechanism. We use a subset of the sequential program model itself of a sequential programming language to represent a state machine textually in the form of a program. So, two approaches to capturing state machine model with sequential programming language. Use a front end tool approach, additional tool installed to support state machine model, graphical and or textual state machine languages. So, we will use a graphical and or state machine languages, and that may support graphical simulation. So, why graphical simulation? Because at that level itself we can up to some level we can understand whether what we have specified is correct or not. And there will be an automatically generate sequential programming language code that is input to the main development tool. Okay. So, we have this front end tool which takes it to the sequential program model automatically, which compiles the front end tool is a diagrammatic tool. You have a compiler for this diagrammatic front end tool, which will automatically generate the sequential program model corresponding, and that sequential program can then be fed to the main tool, which will take it to the further levels of design. Now, what is the drawback of this approach? It must support an additional tool, number one, licensing costs, upgrades, training, etc., that will be required. Another maybe another bottleneck could be that is the interfacing with the main tool. So, the sequential program models can be in different languages. Suppose the main tool supports a language which is not output by the front end tool. So, that interfacing between the output of the front end and the input to the main tool has still to be provided. Okay. So, these are the two drawbacks. So, what do we use instead? Instead of using a front end tool, we use a language subset approach. And how does that approach go about? So, in the language subset approach, we use it follows rules or templates for capturing state machine constructs in equivalent sequential language constructs. Okay. So, we have equivalent sequential language constructs to capture different state machine constructs. Okay. Can be used with software example C and hardware languages like VHDL. So, for our unit control, for example, for our unit control FSMD, you can capture this whole unit control FSMD using a sequential program like the following that we have specified here. So, in this we first enumerate all the states through hash defined constructs. So, idle the state idle is hash defined enumerated as 0, going up is 1, going down is 2 and door open is 3. Then you declare state variable initialized to the initial state. So, you have then you have a subroutine for the unit controller, you go into that subroutine and you have a state variable. So, the current state is captured, is held at any time through this variable state, and this state variable, this variable is initialized to idle. So, declared state variable initialized to the initial state idle for our case. There is a single switch statement which branches to the current state's case. Now, at each point in time we use a switch case to branch to the current state's case. So, suppose the current state of the FSM is going up, then it is 1. So, switch going up or switch 1 will take you to the going up state. So, there is a single switch statement which branches to the current state's case. Now, for if it is going up, you go up. In each case, what do you have? You have actions. So, first after you go to going up, what are the actions? Up has to be 1, down is 0, open door should be closed and the timer should be 0. So, these are the actions at this state. And you also have what? There is a set of if then else statement, if statements. Each case checks transition conditions to determine next state. So, what are these ifs doing? These ifs tell you what are the conditions for going to the next state. For example, if you are at going up, then it says that if rec is still greater than the current floor, then you remain in going up. If rec is not greater than current floor, you go to door open state. Okay. Now, you instead of this if statement, you can make it an explicitly an if then else. You can make it an if else statement, so that even if by mistake you do not have exclusive conditions. So, we said that at any state only one transition should be true. There cannot be a set of inputs which give you a condition where more than one transition becomes true. You cannot have that case. So, suppose by mistake your conditions are such that your design is such that your inputs are such that it allows two transitions to be true. Now, if you specify this, you capture this through an if else and not if, then only the first of these two transitions will be true and not the subsequent ones. Okay. So, you can use an if explicit if else instead of a if. So, this if condition then next state, this structure gives you the way how to go to a next state based on condition. So, what is the general template for designing any state machine using the programming language structure? Again, you have to define or enumerate all the different states in the state machine. Then you have to define a state variable, here state, which has to be first initialized to the initial state. Then you have to go to an infinite loop, in which you will have a single switch case statement. In this switch statement, you will go to the case for the current state based on the value of state. Okay. At each case statement, what do you have? You have the the actions that you have to output at that state, and you have the transition conditions. So, insert transitions for leaving that state, okay, and you break. So, this is the general template. Now, to further succinctly and nicely represent even more complex embedded systems, further extensions to FSMD were specified. One such very important extension is the hierarchical concurrent state machine model, or the HCFSM. So, HCFSM is an extension to state machine model to support hierarchy and concurrency. Now, in this, states can be decomposed into another state machines, or you can say that a state machine can be a whole state machine can be abstracted as a single state. Okay. So, this allows, so this is the hierarchy in the hierarchical state machine. States can be decomposed into another state machine. So, we have a single state and that get decomposed into a complete new state machine. With hierarchy and identical with hierarchy has identical functionality as without hierarchy, but one less transition Z in this case. So, let us see here, we have a state machine without hierarchy. This state machine has three states, A1, A2 and B. The initial state is A1 and you move to state B whenever you have this input Z. So, on input Z, whenever you have this input Z, you go to state B, and at state B, whenever you get this input W, you go to A1 state. Okay. Now, this one is a general state machine that we have studied so far without hierarchy. How do we represent this same state machine with hierarchy? Now, we have clubbed the states A1 and A2 into a composite state A. Okay. So you have now at the outer level you have two states A and B. A is the initial state. Within A1 is the, so within A, this A is basically the state machine composed of two states A1, A2, of which A1 is the initial state. Okay. Now, from this state A, whenever you have this state Z, you move to state B, and whenever you have this state, whenever you have this input Z, you move to state B, and at state B, whenever you have this input W, you move back to state A and to the initial state of A, which is A1. So, in this one, corresponding to this design with hierarchy, it has the same functionality as without hierarchy, but it has one less transition for Z. So, here you had two transitions from A1 and A2 to B, now it has a single transition from the entire state A. So, this one is known as an OR decomposition, because either A or B will be executed at a given time, not both concurrently. So, A and B could possibly be another state machine internally inside B, because B can either also be a composite state. And when you have an OR decomposition, as in here, you say this to be an OR decomposition, because either A or B, the system will be in either state A or state B and not both together concurrently. However, HCFSMs can also have concurrent states, and this is called an AND decomposition. For example, in this case here, you have a state B which has two substates C and D. Each of them happens to be a composite state. C is a composite state which contains a state machine composed of states C1 and C2 and these transitions here. And also you have this composite state D, which is again a state machine composed of states D1 and D2 and these two transitions. Okay. And this is a composite, this represents concurrency, because C and D execute concurrently together. So, both C and D execute concurrently within state B, and because both of them is executing concurrently, we say this to be an AND decomposition. So, C and D execute together. A or B executes together in this example, A or B, this is C and D. So, a language which actually represents such an HCFSM is the state charts. It is a graphical language to capture HCFSM. It has all the functionalities that we just described, and it also along with this, it also allows the function, a function called timeout, which how does it help? Instead of using an explicit external timer, it will remain in a state for a certain amount of time till the timeout happens, and then move out of that state to the state where this timeout label indicates to. It will move to that state after the timeout happens. And it also remembers history. So, it remembers the last substate or decomposed state A was in before transitioning to state B. For example, this is with respect to this example that we were discussing. Now, you can move to state B either from A1 or from A2, because on transition Z you have moved to state B. Now, by remembering history, you remember the last substate from which state in state A, in this state A that you were in before moving to B, before moving to state B. Suppose you move to state B from A2 through using this transition. Now, because you remembered the last substate from which you moved to B, after you go back to A, you can move directly to A2 and not to A1. So, the original HCFSM did not remember history. So, whenever you move from B to A, it will actually go to the initial state of A, which is A1. But state charts provide you the option of remembering history. So, you can go back to either A1 or A2. So, return to saved substate of A when returning from B instead of the initial state. This is allowed by the state charts. To show an example which uses such hierarchy, we extend the specification of our elevator controller by one step. So, let us say that we have a fire mode, and this fire mode, when fire is true, we move the elevator to the first floor and open the door. This is what we have to do. So, how do you capture this without concurrency? You have explicit fire transitions. See, fire transitions. you have explicit fire transitions from all the states of our original unit control FSM to a new state called fire going down. So, when you have a fire, you go to fire going down. In whichever floor you are, you go to the first floor and you open the door after you go there. So, when up till you are going down to the first floor, your open is 0, your down is 1, okay. Your up is 0. So, you cannot go up when you have a fire, you have to go down to the first floor. Your lift door or the elevator door will remain shut. So, open is 0, but down is 1. Now, from there when floor equals to 1 is reached. So, till floor is greater than 1, you move in this self loop and remain in fire going down. So, when you have come down to the first floor, then you open the door, so your up is 0, your down is 0. So, you remain stationary in the first floor and you open the door, and so open is 1, okay, until you have fire. So, after you do not have fire, then what happens? Then when the fire is extinguished, you go back to the idle state of the original state machine. So, when you have fire, you will have explicit fire transitions from each of the states of the original state machine to the fire going down, in which case in the fire going down, it will the lift or the elevator will progressively go down to the first floor. With the door remaining closed, it will go down to the first floor, then it will remain stationary, open the door and remain in that state until fire is on. When the fire is extinguished, it can take fresh requests. So, it will go back to the idle state of the original state machine. So, without hierarchy, this whole thing, so many transitions going on, it is a bit messy. Now, when we have hierarchy, we can model this whole FSM with two hierarchical states. So, we now have two composite states, one is the normal mode and the other is the fire mode. So, the normal mode is our original machine and we move to the fire mode from the normal mode. Whenever there is a fire, we move from the normal mode to the fire mode, and whenever the fire is extinguished, we go back to the initial state of the normal mode from the fire mode. Okay. So, with hierarchy, things become much more simpler to represent. Now, how do we represent concurrently? This whole elevator controller with this unit control, so this is the unit control and request resolver. These two execute concurrently, because these are two modules which execute concurrently. Unit control and request resolver execute concurrently together. Within unit control, you again have this normal mode and fire mode. So, this normal mode and fire mode, this is an OR decomposition of unit control, and you can say of the elevator controller, the unit control and request resolver is an AND decomposition of the elevator controller, because unit control and request resolver executes concurrently. Within unit control, normal mode and fire mode are OR decomposed. Now, after HCFSM comes the program state machine model. It is an extension of the HCFSM. Now, within a state, we can have sequential programs. We can write programs instead of a state diagram. We need not have a state diagram inside a state now. A state can now constitute a program. This is how the program state machine extends HCFSM. Programs, actions can be FSM or a sequential program. So, it can still be an FSM like HCFSM, or it can be a program. The designer can choose whatever he wants. It has a stricter hierarchy than the state charts, in the sense that transition is now only allowed within sibling states. So, if you have between sibling states, that means you suppose you have a particular, so unit control is a composite state within which sibling states are normal mode and fire mode. These are two sibling states. So, now transitions can happen within only these sibling states. So, transition cannot happen between non-sibling states. You cannot go in inside a state within normal mode. Say suppose this normal mode was implemented as an FSM and it had multiple states. You cannot go from a state from fire mode to a state inside the normal mode. Okay. You can only move between sibling states. A program state may complete, that means you go to the execute the end statement of the program, reaches end of the sequential program, or FSM transition can be a special complete substate where you mean that you want to immediately exit based on a condition. So, therefore, PSM has two types of transitions. One is transition immediately, TI taken regardless of the source program state, or transition on completion where the program completes, which would mean for us it goes to, for suppose in fire mode, the program completing will mean that you go to the first floor and only then if the fire is extinguished, then you move from after the program completes, you can move to the next state. So, transition can only be on completion. So, taken only if condition is true and source program is complete. So, fire is extinguished and you reach to the first floor, only then you can go to the normal mode, otherwise not. If you use the TOC extension. So, normal mode and fire mode here, if you can see, are described as sequential programs, not as state machine. So, in the fire mode also you have up equals to 0, down equals to 1, open equals to 0, these variables are initialized. While floor floor get greater than 1, you wait and the elevator progressively moves down. So, when this condition becomes false, that means floor 1 is reached, you make up equals to 0, down equals to 0, that means you stay in the first floor and you open the door. So, this is a sequential program representation of the fire mode. Okay. The black square originating within fire mode indicates that not fire is a TOC transition. It says that not fire is a TOC transition, meaning that this transition will be excited only when the program completes. That means you reach the first floor, you reach floor 1 and only then can this transition be excited. Okay. Transition from fire mode to normal mode only after fire mode is completed. So, this is what it means. State charts is an extension of VHDL to capture the. So, state charts is a language which extends VHDL to capture the PSM model. Similarly, SpecC is a newer language which extends C to capture the PSM model. So, with this we have learned the essential ways of modeling using state machines and the sequential program model. We have seen how concurrent behavior can be represented using hierarchical concurrent FSMs and the program state machine, and how things can be nicely all the entire embedded system behavior can be represented in a structured and systematic manner. With this we come to the end of this lecture.